This is another effect based on electromagnetic induction. It's known as eddy currents, and the application we're using it in is electromagnetic braking. What we have here is a pendulum that consists just of a sheet of aluminum swinging like that, and as you can see it swings quite happily. When we flip over this magnet, which has quite a strong permanent magnetic field, you'll notice that it stops almost instantly. Let's do it again. And in fact, if you move it like this, you can actually feel there's a fair bit of resistance, and the faster you move it, the more resistance there is. So we'll see this arises from the effect known as eddy currents. You'll also even see the following effect, that if we flip the magnet quickly, we can actually start it swinging. No physical contact at all, it's simply an induced current in the aluminum. To convince you this is real, let's look at two variations on this experiment. I have to take out the solid piece of aluminum, and I'll put in this piece that has a comb structure on it. We can start it swinging again. Now, I'll show you that again. What you'll notice is that as this bit where the comb, tines of the cone are, swings through it, there's effectively no braking. There will be some braking when this part goes through. That's because in this part we can't have an induced current flowing because there's a break in the circuit. In this part we can have an induced current, and it'll flow around those loops there. So again, so you'll notice the braking occurs when we have this where the current can flow, but not where we have the comb, because then you can't have a continuous current. Final variation on this is to use a sheet of non-conducting material. We can more or less predict what's going to happen in this case. If we've got a non-conductor, even though it's moving in a magnetic field, there cannot be an induced current. The induced current can't flow. That's not to say there's no induced voltage. There will in fact be a voltage in this sheet of perspex. It's a very tiny voltage, but in fact there will be no current. If there's no current, there's no electromagnetic braking, and hence it won't stop. And you notice there's no effect at all. This has some practical importance. If you want to stop a train, you can use, of course, friction brakes just as you can in a car. But the problem with this is that friction creates dust. There's wear on the brake pads. Most of the time this doesn't matter, but it does matter if you're in an underground train, in a metro in other words. So you'll find that most metro systems in fact use electromagnetic braking, firstly because it's more efficient, but secondly because it produces no dust in the process, which is quite important if you're underground.